it's Mr. Reedy back with yet another video. Today, guys, we're going to talk about the reaction quotient. Okay, so thus far in this chapter, everyone, we have discussed particularly when a reaction has reached equilibrium. But the question is what if the reaction is not at equilibrium? So we can use this thing called the reaction quotient to gauge the process of a chemical reaction to see where it is relative to equilibrium. Okay, so with that in mind, the reaction quotient has the exact same definition as the equilibrium constant, except that the reaction does not need to be at equilibrium. So let's consider the generic chemical equilibrium. AA plus BB is in equilibrium with CC plus DD, where of course the capital letters here are our substances and the lowercase letters are our stoichiometry coefficients. The way that I would write the reaction quotient would be the same way I would write the equilibrium constant, except again, I can now take any pressure, any partial pressure, or any concentration throughout the process of the reaction and see where that reaction is relative to its equilibrium by calculating the reaction quotient. So the reaction quotients are given to you here. Of course, we have it in terms of concentration with QC and then in terms of partial pressure with QP. Again, you would write the reaction quotient the same way you write the equilibrium constant. Now, in terms of the reaction quotient, why is it important, or what's different about it rather than the equilibrium constant? Well, the first difference is that the equilibrium constant is going to be constant at a given temperature. Okay, we saw that in the last couple of topics, that the equilibrium constant is dependent on temperature, therefore it's constant at a given temperature. Now, with that in mind, the reaction quotient can change based upon the current state of the reaction. So the reaction quotient changes in an equilibrium where the equilibrium constant itself is constant at that given temperature. Okay, so keep that in mind again, because the reaction quotient is telling us where the reaction is relative to equilibrium. Okay, so as a couple examples, when the reaction mixture contains only reactants, then QC will be 0. If the reaction mixture contains only products, QC will approach infinity. And when the reaction mixture contains a mixture of reactants and products each at 1 molar, then QC is equal to 1. Okay. But the most important thing, guys, on this slide is what's highlighted in blue, which is at equilibrium, the reaction quotient is equal to the equilibrium constant. And that fact here, guys, is how we're going to judge where the reaction is. So looking at the graph here, okay, when Q is less than K, so when Q is less than K, right, smaller than the equilibrium constant, the reaction is going to proceed to the right. Okay, so it will favor the forward reaction or it will proceed towards the products. Okay, when the reaction quotient Q is greater than K, so like right around here on this graph here, the reaction is going to favor the reverse reaction or will proceed to the left, aka will go to the reactants, excuse me. Finally, when the reaction quotient is equal to the equilibrium constant, like right here at this point, the reaction has finally reached equilibrium. And as we know, equilibrium states that the forward rate of reaction is equal to the reverse rate of reaction. Okay, so very important here how Q and K can predict the rate of the direction of the reaction. So again, when Q is less than K, the reaction proceeds to the right, it favors the forward, goes towards the products. If Q is greater than K, the reaction will favor the reverse reaction, proceeds to the left or towards reactants. When Q is equal to K, we've reached chemical equilibrium. So consider the reaction and its equilibrium constant at 25 degrees Celsius. We have iodine gas reacting with chlorine gas, which is in equilibrium with iodine monochloride. Okay, we have a Kp value of 81.9, and our reaction states a reaction mixture contains iodine gas with a partial pressure of 0.114 atmospheres, chlorine gas with a partial pressure of 0.102 atmospheres, and ICl with a partial pressure of 0.355 atmospheres. Okay. It says that is the reaction mixture at equilibrium? And if not, which direction will the equilibrium proceed? So, folks, the first thing we're going to start off with is writing our reaction quotient. So I'm going to write the reaction quotient for this particular equilibrium. So it's going to be QP. And the reason why it's QP here, everyone, is because we're given partial pressure. So QP is equal to the partial pressure of ICl, and I'm going to square it because there is a 2 in front of ICl in the balanced chemical equation, over the partial pressure of iodine times the partial pressure of chlorine. You'll notice that I don't have to raise iodine or chlorine to any power because there are 1s in front of them in the balanced chemical equation. Now I'm going to plug in my numbers. So I'm going to plug in 0.355 atmospheres for ICl. I'm going to raise that to the second power. Don't forget my decimal point there. Then I'm going to, in the denominator, put 0.14 atmospheres in for I2 times 0.102 atmospheres in for Cl2. And then I'm going to just plug this value into my calculator. All right. After I plug this in, I get an answer of 10.8. So in this case, QP is less than KP, right? So when Q is less than K, the reaction, I'm sorry, I wrote that backwards. So since Q is less than KP, guys, obviously the reaction is not at equilibrium, and then the reaction will favor the right or the products, right? So this reaction will go towards the products, okay? And one thing I have to make sure I really explicitly state here, guys, is this is your final answer for this problem. Yes, you have to go through and calculate the reaction quotient. Yes, you have to state that QP is less than KP. However, the reaction itself, the answer to this problem is no, the reaction is not at equilibrium. And which direction will it favor? It's going to favor the right, so it's going to proceed towards the products. Okay, that's your answer here. Don't make sure, guys, that you're reading these questions closely, because getting just to here, right, getting just to this point, you're going to lose points on the AP exam if you don't answer the question fully. Okay. Let's do another example problem. So it says, consider the reaction in its equilibrium constant below. So we have N2O4 is in equilibrium with NO2 with an equilibrium constant of 8.85 times 10 to the negative 3 at 67.7 degrees Celsius. It says the reaction mixture contains a concentration of NO2 at 0.0255 molar and a concentration of N2O4 at a concentration of 0.331 molar. It says to calculate Q and determine the direction the reaction will proceed. Everyone, what I want you to do now is I want you to pause the video, try to solve this problem on your own, then unpause it to see if you get the correct answer. Okay. Go, folks, I hope you were able to determine that QC is greater than KC, so therefore the reaction will go towards the reactants. You can see my work there above. In this case, guys, it was easier to convert my final answer into scientific notation, so it was an easy comparison. Okay. But with that said, QC is greater than KC, so the reaction is going to go towards the reactants or go to the left. And with that being said, folks, that's the end of today's video. If you have any questions, please feel free to email me.